Well, g'day flatties and globe defenders, it's Critical Think from Down Under. Thank you, that's very kind. Well, today we're going to look at how a 3-foot wave can destroy Flat Earth and Dave. Oh, look at that. I'm a poet and I didn't even know it. Now, some of you have probably seen this. Recently, Flat Earth Dave tried to explain how he thinks a 3-foot wave can block a tall ship from a 6-foot man on a flat Earth. Now, the flatties have to try to explain this because a ship will sail over the curvature of the Earth and dip behind the horizon. And because the Earth must be flat, there must be a flat Earth explanation for this, when in reality the explanation is very simple. The Earth is a globe. But anyway, we'll look at this Flat Earth Dave explanation.
Okay, the question is asked, how can a 3-foot wave block a giant ship from a 6-foot tall man?
Well, the answer is very simple. It can't. Be interesting to see what kind of explanation he comes up with.
Here we have a 6-foot tall guy. We have a 3-foot wave. And this is his line of sight over the wave to where he can see the water. And there's a small gap in between the wave and where he can see the water.
Yeah, that's okay. No worries with that.
Now, we live on a flat Earth.
Wait a minute. No, we don't. But let's just assume we do for the purpose of this exercise.
A 6-foot tall man looking down at the water is looking down 6 feet. If he looks down at the water here, he's looking down 6 feet. Out here, it's still 6 feet below his eyes. But the angle changes. So
that's great, because that's another good test that we can check for a flat Earth versus globe. That as the water goes away, if it's not 6 feet anymore, if it's more than that, then the Earth's not flat. And there are many, many tests like that show the Earth's not flat. But anyway, I sidetrack.
Watch what happens. We move that wave out and look at the gap between where he can see the water and where the wave is. It gets longer and longer. Look how wide it is now. And it's really wide. He's still looking down.
So one of the things is flat earthers don't talk in terms of measurements. So it always gets longer, but how long, how far? These things are very important, but the details are left out for obvious reasons, which you will see.
Now, this was an orthographic view. Nobody sees sideways, but this is...
Just remember that, an orthographic view, nobody sees sideways. Just remember that.
This is what's going on, but this is how we really see. And again, here's an orthographic view again. So we got our boat right here. We got our guy right here. We got our wave. He's blocking the bottom of the boat, but he could kind of look over the wave a little bit. And if we put the ship out here, he can still see the whole ship down to the water line. Farther out, he can still see it. He can still see it. He can still see it. Makes perfect sense. So now I move the wave way out here. Now, even though it's smaller, it's still 3 feet above the flat water.
Yeah, but it's still going to be so small as you move it further out, you're not even going to be able to see your silly wave.
And let's take a look. So here's our perspective grid. It gets this amount of information. Let's say this is 1 mile, right? 1 mile, that's a mile, that's a mile, that's a mile.
Okay, so we count those. 1, 2, 3, 4, 5, 6, 7, 8, 9 miles. So his 3-foot wave is 9 miles out. And he, of course, he's committing the mortal sin of mixing perspective and orthographic views, which is a common problem with flat Earth diagrams. And if this 3-foot wave is 9 miles away, you wouldn't even be able to see it, right? It would not be resolvable by the human eye. That you would need a zoom lens to see it. But anyway, let's carry on.
Those miles are getting compressed more and more and more If I zoom in, each one of these is a mile, and it's getting compressed until they're literally on top of each other.
Now, to be perfectly honest, this makes absolutely no sense to me. But I do know that a lot of flat earthers think this is, oh, yeah, that makes so much sense. And it makes sense to Flat Earth Dave in his mind too. However, I'm willing to listen, and we'll see if we can verify in physical reality if this makes sense.
So when a ship is out here, so let's say it takes 10 minutes, 15 minutes to go a mile, right? 15 minutes, 15 minutes, 15 minutes, 15. Each one of those is 15 minutes. So when it's out this far from your point of view, it's not going to move very far in your visual space. It's
irrelevant.
Still going a mile, a mile, a mile, and a mile.
Yeah, big deal.
But it's staying relatively in the same area. It's just going to get smaller and smaller. This is his line of sight. He can't see the water until over here. So the ship will just shrink and get smaller and smaller. And because all of that distance is compressed into this small space, the boat's just going to get smaller and smaller and smaller, and it's not really going to move farther in your visual space. It's just going to disappear. The entire boat can disappear behind this small wave.
Well, that's not going to happen. And while that may seem a plausible explanation to some people, it's completely ridiculous to me. But anyway, let's go.
On top of that, there's a marine layer. The lower you are to the water, the thicker the air column is. And on certain days, most days, that air column, those few feet above.
So here he's trying to build himself an out when he's proved wrong on this wave thing. Because when we prove that it's not the wave, it's the marine layer.
The water will become opaque over distance, and boats will literally disappear behind that, along with miraging. It's never just one thing, but this is how a 3-foot wave can block a cruise ship.
So except when there's no miraging and this so-called marine layer, which, yeah, right, can happen, but that's why you get higher than 6 foot to make these observations. Means you can eliminate the marine layer. So in places Dave tries to imply that we don't know that the ship gets smaller, which is absolutely ridiculous. Of course, everybody knows the ship will appear to be smaller as it gets further away. Now, the other day, Ruif was on Flat Earth Fridays, and so happens that Dave turned up and said a little bit more about this.
So I actually just made a new graphic because thanks to you guys, the people that are coming at me, saying that I looked at it orthographically and I made it smaller. Yeah, I'm not the greatest graphic artist, but because of your input, I've made a new demonstration. And as soon as I see it, I don't know what your argument will be, but it actually shows how a 3-foot wave can hide Mount Everest.
Right. So a 3-foot wave can hide Mount Everest. Of course, that's quite possible on a globe, but impossible on a flat Earth. And I don't care how you've reconfigured your diagram, it's going to be a load of rubbish anyway. But this is all we've got right now is your diagram now. So we'll continue looking at this. Now, Dave went on to say a few more things.
Dave's 6 feet. So he's above the waves. He's above the waves, right? The wave can block no more than 3 foot on a flat Earth.
No, because the mountain is farther away than you are. The ground ramps up. That's how we see. And as it goes away, it gets smaller. If that 3-foot wave...
You notice that he said there, the ground ramps up. That's very important, and we'll see that later.
It was halfway between me and the thing. No, it won't hide it. But if the object is multiple times distance farther, it's multiple reductions in 50%, 50%, 50%.
So here, when we notice that he says it needs to be multiple times distance away, and he's talking about 50% reduction, but he's made a serious logical error with this 50% reduction, and we'll see about that.
Smaller, and then it will hide behind it. You have to understand
you gave the right answer.
You have to understand it's imagine you're standing 6 foot tall person, and there's something 3 feet right in front of you, and you have a never ending extendable yardstick. So that yardstick goes from your eyes, touches the tangent of the box, and touches the floor. And let's say the distance between the box and the floor is 3 feet. Now we just start dragging that box farther and farther and farther away. The ruler extends longer and longer. You'll watch the distance between the bottom of the box and where it touches the floor. It's going to get longer and longer and longer and longer.
No, you can't watch that. Remember, we don't see in orthographic. That's what you will see in an orthographic view. If you are the person looking at the box, you won't be able to tell where this theoretical long pole is parallel, whether it's parallel or not parallel, how close it is to the ground. You won't be able to see any of those things. That can only be apparent on an orthographic view.
And there will be a point where I can't even determine that line isn't parallel from the ground. It'll look parallel when I get that 3 foot box, I don't know, a mile away, 10 miles away, whatever it is.
No. You're not looking orthographically. You won't be able to tell that.
And that line to me will look parallel, right? So if I put a 6 foot box right on the far side of that, and I started dragging it away, it's going to get smaller and smaller, and it will be underneath that ruler, that line, as it gets smaller, but it has to be multiple times distance farther. I don't know why you.
So no, it will never get below that line. And now he's saying about it must be multiple times distant, and how we somehow don't understand this, that things get smaller as they get further away. But what he doesn't understand, that smaller does not mean behind. Okay? Smaller does not mean behind.
You guys can understand that. You're not listening. I'm going to say it again. So let's say we move it infinitely far away, and now it's touching the cruise ship at 3 feet. Okay, perfect, great. Right. And to me, that yardstick
looks. So it didn't block it, right?
Let me finish what I'm saying. So to me, that yardstick from my eyes to that ruler at whatever that pretty far distance is looking pretty parallel to the water. We can agree that I probably can't discern that it's not parallel because it looks parallel. But
how can it look parallel when you're looking down the length of the yardstick? I don't know.
It's only touching the cruise ship at 3 feet because the cruise ship's right next to it. So let's say that distance is X, whatever it is. And I move that cruise ship.
Again, notice the complete lack of examples by numbers, because if you don't put the numbers in, then you can make up whatever you like. It's the numbers which can tell you, does it work in reality or not?
Ship 2x away. Well, now it's touching the cruise ship from my point of view higher. No, it's not. It's still touching. No, you're right. I'm sorry, I said that wrong. It's still touching it at 3 feet, but the cruise ship is getting smaller.
Here we go again with this. It's not going to touch it higher. But how can the top of the cruise ship get below the top of the 3 foot wave if the 3 foot wave does not block higher than it did before? So there's a contradiction there. So
the cruise ship from when it's right next to the box is, let's say it's 300 feet high. If I move it twice the distance away, the cruise ship's only 150 feet high. If I move it one more segment, in angular size from the ground up, from my point of view,
is not an angular size measurement.
Well, I'm telling you, its angular size is getting reduced by 50% every time I move it one segment farther.
Dave uses the word segment here, so they're not equidistant segments. So let's say 4 kilometres is one segment. So 2 segments is 8 kilometres. 3 segments is 16. 4 segments is 32.
It's going to get reduced. Now, I get it. In your math, you don't understand how that happens, but it does.
Oh, really? In our math? You mean there's a flat Earth math and a globe math? How come we never see the flat Earth math? What's the definition of flat Earth math and globe math? Is globe math any math which might happen to prove the globe? Huh? Oh, and flat Earth math, we can make it up as you go along, like 1 and 1 is 3, if that happens to fit the flat Earth. That flat Earth math? And no, our math doesn't understand perspective. Our math is the one that calculates perspective. Our math is the one that tells you how big or small something will look in angular size. That's our math. What can your math do? Your flat Earth math. Can it predict the angular size of something at a certain distance? I don't think so.
Does happen, and it will get smaller than the angular size of my much, much, much closer 3-foot box wave.
Yeah, but you haven't answered. How far away does it have to be before it gets that small?
Does the cruise ship get smaller as it moves farther away?
In angular size, yes.
Okay, angular size. It gets smaller in my view. Let me ask you another question.
So does the 3 feet.
The 3-foot box. The 3-foot box, does it get smaller when it doesn't move any farther away?
No.
Okay, so if I move that ship away, it is getting smaller and smaller and smaller, while my 3-foot box stays the same height. You can actually do this and actually see it happen yourself with a physical model on a floor, right? You can also draw the graphics and do it and slide that box out across.
Okay, so he said we can do it. Demonstrate this as a physical model or graphics. Sounds like a good idea, Dave.
Across your screen and watch that angular tangent line go right over the larger ship.
Okay. So, yeah, okay, I took my camera out and tried to find a suitable place to try and demonstrate this. But I really couldn't find something that was bulletproof, you could say. For starters, I think you're going to need a very long piece of flat surface, because Dave talked about doing this in Home Depot or something like this. And the places I could find first, they had to be guaranteed flat, and that's not so easy. And second, the distance, no matter the distance I chose, it would not be long enough for the flat earthers. They would just say, oh no, you didn't push the 3-foot box or wave or whatever you got. You didn't push that 3-foot box away far enough, and you didn't push the ship far enough. So I thought, no, well, okay, Dave said we could do it in a model, so I've built a model for this. Here we are with my favourite modelling tool, Blender. Now I've got this ship, or what could be, if you use a little bit of imagination, it would be a ship, but it's almost a ship-size object. I didn't make it as tall as a cruise ship because it doesn't need to be that tall. A lot of ships are around 35 to 40 metres high. This one I've made is 35 metres wide, and it's only 19.9 metres high. So it's just not as tall as 320 feet, but this one is better, right? This one's small. It should hide behind the wave much easier. So that's roughly 20 metres, or what's that? Only 60 feet. Should be a piece of cake to hide it behind our 3-foot wave, which this is my 1 metre wave here. It's 1 metre high, which is roughly 3 feet. Now I've got my camera. My camera is over here, 6 foot above the ground. So that's 2 metres, so roughly 6 foot. So I've got a 1 metre wave there. I've got my eye at 2 metres above the ground. So the this flat surface goes on. See how many metres that's 400 kilometres of flat surface. Now, I could make it further, but I don't think we need that in this demonstration. So we've got 400 kilometres of flat surface. You're looking down the bottom here, you look through the camera, and this is what you see if you're 2 metres high or 6 feet. And at the moment, I've got the wave, which is the blue wave, there is 90 metres away. And the cruise ship is... where are we? How far away is that? That's 100 metres there. And so now, all right, that's pretty close. You can see it all. Here you can see them. Now let's move. Now, Dave talked about moving it like 9 miles. Well, 9 miles is just too far. For starters, isn't the horizon supposed to be at 3 miles? You know that horizon, that thing that you can't form on a flat Earth, that can only be formed on a globe? That one? That horizon is only 3 miles away. Now, according to Dave, his definition of a horizon is when these checkered things get so small you can't distinguish one from the next. I think that happens pretty quickly here, but you can still see the flat surface beyond that, and that's only 400 kilometres out. So just imagine if that stretched a few more thousand kilometres, it'd be a little bit extra, but not much. So anyway, I'm going to put my wave, I'm going to put it in front of the horizon. So I'm going to shift this wave, or about 4 kilometres out. 4 kilometres. So now the wave's shifted back. I've got to shift my cruise ship back. Or let's just start with 8 kilometres. All right. Now we're going to need to get out our P1000 camera now, because now they're very small and you can't even see the 3-foot wave anymore, and you can barely see the cruise ship. So we're going to whip out our P1000 and zoom in. Righto. So we have, this is about a 2,000 millimetre zoom. We can see our ship and we can see our wave. Already I see that there's a bit of a problem. We're starting, rather than having the ship blocked by the wave, we're starting to see the bottom of the ship. I think that's a bit of a problem. Okay, so it's because the ship is not small enough, isn't it, Flatties? So yes, well, we better shift the ship away one more segment. So the ship is now 8 kilometres away. Now you've got to understand that on the globe, this will already be over the curve and you'll be starting to see bottom-up obstruction. But on your 3-foot wave can block a ship model, that's just not working. I'm still seeing the ship, and I'm actually seeing more of the ship, not less. I think there's a bit of a problem with your hypothesis there, Dave. Now we'll make that 16 kilometres. We'll double the distance. We should halve the angular size of the ship. There we go. Yep. Oh my God, let's just zoom in a little bit more. And we're starting to see water now. Water between the wave and the ship. The ship has become fully visible. So if we whipped out our P1000, there's maximum zoom there on a P1000, we'll see that the wave does not block the ship. In fact, there's water. You can see water in between the top of the wave and the ship. Oh, that just doesn't work. Your hypothesis is broken there, Dave. A wave cannot hide a ship. Now let's move this ship further away until it's similar size to the wave. Now, this would be 140 kilometres or thereabouts. 140 kilometres. There's the ship. Yeah, that looks about similar size to the wave. Now, by this time, on our globe, the ship would be well over the curve and you couldn't see it. Now, according to Dave and other flat earthers, then this ship should be behind this wave, but it's not, you see. Dave, you forgot about the ramping, right? You remember the ramping that you mentioned? The ramping goes up. That includes the area of the flatness behind the 3-foot wave as well. So that means the ship ramps up too in your eyesight, in you, and so it ramps up above the 3-metre wave. 3-foot wave, 1 metre. So there's a bit of a flaw in your argument there, Dave. I think you're going to have to rethink this. It looks like the Earth is not flat after all, and the globe perfectly describes what we see. But your flat Earth hypothesis is completely broken.